Xin, and I'm a PhD student at University of California, Santa Cruz, and my advisor is Roberto Manducci. And our work is called a Fast and Robust Text Spotter. So in this work, we focus on syntax detection. Syntax detection is a very challenging problem because like different variants of fonts and illumination, and also the background could be very complex. And it has a very wide range of applications such as assistive technology for blind people and video surveillance and image and video retrieval and navigation, etc. So this is our pipeline. Our pipeline is, so we structure our algorithm as a cascade classifier. So at the beginning, we extract some candidate character regions proposed by a feature extractor called MSER. And it's a very common used method to propose candidate character regions. So to increase the recall at the beginning stage, we run MSER on 7 color channels. And so on average, there are about 3,000 bounding box extracted from 7 color channels using MSER. And also we use a very conservative threshold for MSER to increase the recall. But we noticed that there are a lot of heavily overlapping and nested MSER regions. And so it's not wise, it's not very smart to throw all of them to a CNN classifier because CNN classifier is not that computational expensive. It's not that computational, it's very computational expensive. So our contribution, first our contribution is we propose a very simple but effective way to clustering and pruning MSERs with very minimal performance drop. And then we feed this binary MSER mask to our CNN classifiers. And finally, we group candidate regions into text lines. So this is our first contribution. So we group heavily overlapping MSERs into clusters. And in the middle image, we only show a cluster that contains more than 2 MSER regions. So compare with this 3,000 bounding box, we already throw away lots of MSERs, but notice that all the characters are still there. And MSERs from the same cluster was labeled using the same color in this middle image. Okay, so now we have clusters of MSERs, and we could potentially throw all of them into a CNN, but I think we can do better. So our idea is we want to find one representative MSERs per cluster. So to do that, we define a new measurement called fullness. So fullness is the size of MSER mask divided by the size, aka the size of, look at the right image, bottom line, and aka the size of the black pixels, the number of black pixels divided by the size of this, its rectangular bounding box. So in the red image, we saw several MSERs that from the same clusters labeled by the red rectangle on top. And we order them by descending orders of fullness. And we can see that the one with maximum fullness is a great choice for being the representative because it's corresponding to an over segment result and it has a very strong and clean stroke. So it's a good choice to be representative. So the next step, we throw this. So instead of feed the binary value patches to CNN, which most previous method does, we throw the binary mask to the CNN, and we achieve a significant performance boost. I think mostly for 2 reasons. First of all, the binary mask can throw away can get rid of this clutter background and make sure the CNN learns the shape of the MSER, not the features from the clutter background. And also, this binary mask significantly boosts the contrast, like for example, the E. So our CNN structure is a toy structure, only contains 2 convolution network, and we find this like good enough, and there's no need to go in deeper. And we also propose a new method to mine binary training samples from only image with word level notation. Okay, so here's some results. And the bottom row is the corresponding heat map we produced. We achieve state-of-the-art results on XR benchmark while being reasonably fast.